physical science students, I'm going to go through the history of atomic structure by the models that we've accepted or adopted throughout the years. It's going to be similar to what we've already talked about with the different people and what they contributed. I'm going to leave that there because I need water, so I'm going to stay hydrated. Anyway, let's start out with the very first model of the atom that we had. Kind of started with Democritus. He was the first guy to say, you know, we can't just keep dividing matter indefinitely. At some point, we're going to get to something that can't be divided any further while still having the same matter. So basically, this would be Democritus, or the guy that came up with the real theory was Dalton. And he had a couple points to his theory that all atoms of the same element are exactly alike. They didn't know what they looked like. They didn't have a clue that he was very right about that all carbon atoms are carbon atoms because they have 6 protons, and nitrogen is nitrogen because they have 7 protons, and et cetera, et cetera. He also said that atoms combine with other atoms to form new substances. So that's where this water would come into play. He knew that this oxygen atom looked like all other oxygen atoms. He knew that this hydrogen atom looked like all other hydrogen atoms. Those two hydrogen would look exactly the same, but then they combine somehow to form something brand new. So we went from oxygen and hydrogen, which are gases, to water, which is a liquid at room temperature. And that's what we accepted for a very long time. And then along comes, move this water out of the way, along comes Thomson, J.J. Thomson. And he was messing around with this cathode ray tube, and he was emitting a stream of electrons from the cathode. All right, let's draw this up here. So we have this little cathode. A cathode is something that emits negative particles. And so he was emitting these particles, and then he was shooting them onto this screen that could tell where it hit. When it would hit, it would light up, some phosphorescence, something, I don't know. And then he would put a positive charge plate here, a negative one here. He'd flop them around. And he noticed that this stream without these charged plates would go straight and hit right there. But with a charged plate, it would bend slightly. It always bent toward the positive and away from the negative. So if he were to flop these around, put a negative down here, a positive down there and a negative up here, it bent this way. And he tried all sorts of different metal for this cathode, and it ended up being the same. He could also get it to bend with a magnet. So he discovered that we don't have just this hard atom that can't be split. It has a negative aspect to it. So he came up with this thing called the plum pudding model, where all of this is positive, and then these negative things are just kind of stuck in there, like plums in plum pudding. Lorelei showed me a picture of plum pudding. It looked okay. I don't know. I think, yeah, whatever. So he called this the plum pudding model. Now, our atom that we thought was indivisible actually is made up of smaller parts, this negative part, and he called it an electron. And he also got very, very, very close estimating the mass of that electron. It was about 2,000 times smaller than a hydrogen atom. And that's true because a hydrogen atom is just a proton, and an electron is 1,836th of a proton's mass. So he was pretty dang close. So that's how we got Thomson. And then old Rutherford, using his gold foil experiment where he was shooting those alpha particles. An alpha particle is it's the result of radioactive decay, but it is 2 protons and 2 neutrons with no electrons. So it's the nucleus of a helium atom. If you look on your periodic table, helium is number 2. It has 2 protons, and then most helium atoms have 2 neutrons as well. So that's what an alpha particle is. He was shooting these through a very, very thin layer of gold foil, and most of them passed right through, but some of them would be bent. Their path was diverted somewhat, and some bounced right back. And so he realized it can't be, the atoms in that gold foil cannot look like this. There has to be something very, very dense and very, very positively charged to deflect this positive charge. And the positiveness is spread out throughout the whole thing. And he said, no, that positive is in the middle. It's very, very dense. So all of this positiveness is now confined to a much, much smaller space, and the electrons are outside. So this would be our current Rutherford. They couldn't really explain why these electrons wouldn't be sucked into the nucleus, because unlike charges attract each other. I'm a little bit distracted right now because I'm sitting at my counter in my kitchen, and one heck of a little squall is going through right now. And it's raining and it's nasty out there. And I hear the wind whipping through my vents. Anyways, so this is the Rutherfordian. So we've gone from just something that cannot be divided any further at all to something that does have a negative aspect to it. We thought it was just kind of stuck in there, to a nucleus, which is a very dense center to the atom, positively charged. And then Bohr. What Bohr did, it's a little bit more difficult to explain, but he was just shooting electricity through a tube that contained hydrogen gas, and found out that this would emit light, just like a white light. But then when he put that light through a prism, it divided into 5 different colors, 5 or 6. I said the same thing in the last video. I said I couldn't remember and I didn't look it up. But anyway, more than one color. So he realized that since hydrogen is 1 proton surrounded by 1 electron, I'm going to make the electron like that. That 1 electron, how could that electron emit more than 1 different color? It's only 1 electron. But if it is falling from different levels outside the nucleus, each time it would fall from this level to that level, because that's what happens when you put electricity through a gas. And I have some tubes at school, and when you're in chemistry, I'll show you these. They always glow different colors. And what happens is the electricity causes these electrons to get super excited. They get a lot of kinetic energy, and they get farther away from the nucleus when they do this, until they can't gain any more energy, and then they fall back down. When they fall back down from one level to another, and this is what Bohr was thinking, that there are levels outside of the nucleus based on the amount of energy the electron has. When they fall from one level to another, as they lose that kinetic energy, it comes out as light. So falling from this level to that level would be 1 color of light. Falling from this level to that level would be another color of light, because remember that light, the different colors are different frequencies, and those that have higher energy are going to be a higher frequency. So the main thing you have to gather from this is that we no longer have these electrons just flying around out here. There's a little bit more of a choreographed dance. We've got our positive nucleus, and then we're going to have electrons either in this level, and there's up to 7 levels. So now this is what we call the Bohr model. This is normally what I draw as the Bohr model, but we actually go a little bit further than that, because within each level there are areas of high probability where they can be found. This is where Schrodinger and Heisenberg came in with their studies. These areas of high probability are called orbitals. And what you don't need to know this year, but I'm laying down some tracks for when you do take chemistry. The orbitals are different shapes, and each orbital can hold 2 electrons. So we have an orbital here called an s orbital. It's spherical shaped, and you'll have 2 electrons that you find in there. High probability areas where you might find them. The second level is going to have an s orbital, and it's going to have 3 p orbitals. The next level, I'm running out of room here, is going to have an s, spherical shaped, 3 p's, which are kind of double dumbbell shaped, and 5 d orbitals, and they are double dumbbell shaped. This always takes me a while. I start out really good, and then I start losing control of my pencil. And the number that each orbital comes in is based upon its possible orientation in space. Again, you don't need to know that. I don't, 1, 2, 3, 4, 5. Okay. I don't draw these models. That's just a little bit too complicated. When I'm drawing models, I stick with just the Bohr model. This is more of an accurate model. And it's not really called, it's the Schrodinger Heisenberg. It's just our most accurate model so far. I do want to show you something though. When I draw a Bohr model, and you'll see this, I'll draw some coming up in our video lectures. I always put the same number of electrons in each level. The first one I always put 2. The first level has an s orbital, and each orbital can hold 2, so that's your 2. The second one, how many did I put in the second one? 2, 4, 6, 8. 2 in this s orbital and 2 in each p orbital. 2, 4, 6, 8. The next level can hold 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Each orbital can hold 2. But basically, I just wanted to show you the history of where we're at with our current atomic model. This is the most accurate one, but this is the one you're going to see me draw. Sometimes you'll see me draw them like this. Let's make this oxygen. All right, 8 protons in the middle. I'm going to make it neutral, so I'm going to have 8 electrons as well. I'll do this. I'll put 2 s's to represent 2 electrons in the s orbital. And then there's 4 total electrons. And you'll see that I always do something like this. And this is a little thing called Hund's rule. Again, you don't have to know it, but 2, 4, 6, 8. Oops. Yeah. I don't need that. So it actually would be like this, excuse me, following Hund's rule and then putting too many electrons. So you have to have 1 in each p orbital before it doubles up. And again, in chemistry, you're going to go, oh, I remember your stupid video you did during COVID high school. You talked about that. So 2, 4, 5, 6, 7, 8. There we go. That would be how I would draw it. It's kind of a hybrid between the orbitals and the Bohr model to let you know that the first 2 are in the s, these are in the s, p's, okay? If we made this fluorine 9, we'd toss another one in there. If this were neon 10, and just so you know, s's are full, all the p's are full. That's a really happy state for atoms. This is what we call a noble gas configuration. Find neon on your periodic table. What family does it belong to? The noble gases? That's kind of cool. Anyway, drink your water. See you on the other side.